a topic of mountain movement substance for the rest of your engineering career, actually, if you get the idea. So I recommend you to get the idea, because I'm going to try to teach you some specific things that I'm going to check in this course that you can do within our level course. But the idea and the principles of what I will share with you today is something that can be used beyond this little thing that I'm going to... So there's a general thing and there are some specifics that I teach you as an application of the general thing. And I made the link too. I'm not going to try to read or tell about Baron von Münchhausen yet. Det kan I selv gøre. You can do that yourselves. Das kann ihr selber machen. Very interesting. He could do different things, and that's of course completely the full and only truth. He could, for instance, pull himself up by the hair roots. He had a problem with jumping over a swamp at some time, and the horse didn't jump far enough, so he just turned around in the air and moved back and tried again. And then the second time he tried, he thought it was okay, and he fell into the swamp. And basically, he had the problem, he was almost dying, so he dragged himself out by the hair roots and survived yet again an interesting event in his life. And this is the kind of tool that I'm going to share with you today, to the level of being able to save ourselves from almost basically anything out there that will hit us, right? Be prepared. The boring name of it is simulation-based statistics. We have a plan for the 2 lectures, a few titles for the first part. This is basically the first part, and then a lot of titles for the second part, because there's a lot of repetition there, but that's how it goes. I'm going to introduce to you what simulation really is. We've already used it a lot in the course, and maybe you've used it also in other courses. So, but let me motivate it just a little bit more. Why we take it up in this course, and maybe why we take it up now. Maybe we need to think about what we've learned in this course so far. You have learned, if I may say it in a everyday way for a guy like me, I would say, I have taught you to do statistics in 1 and 2 sample situations, 1 and 2 sample settings. That is either with 1 column of data or 2 columns of data. I have taught you how to do statistics. What do I mean when I say how to do statistics? I mean compute confidence intervals, do hypothesis testing, right? Mostly for the means of those 1 or 2 samples, and just a little bit for the variance also, but mostly for the means, right? So I've taught you to do statistics on 1 and 2 means, basically. How did we do it? We basically used the t-distribution for finding p-values and quantiles for the confidence intervals. And then for the variance, we used the chi-square distribution, right? That's the tools I gave you, summarized into 2 or 3 sentences. Now, why is that, in a way, not enough? Well, I think you know by now, probably you knew, that in your engineering career you cannot cope with just looking at 1 and 2 means, right? The world out there is more complicated and more challenging for you. So, we may compute many other things than just the means out there in the future. I call it maybe statistics, or we could call it features, computed features, and such things. If we want to do, and we should, if we want to be intelligent about empirical information out there, we should think about statistics. And we should, what is another word for that? That is to say, we should think about sampling distributions. We need to think about how different could this thing that we compute be next time that we compute it. That's the intelligent idea of this whole course, of the basic statistics idea. I just mentioned a few here. Maybe we compute a trimmed mean. Do you know what a trimmed mean is? I didn't sort of suggest it to you, but that's where you throw away the most extreme observations, for instance, the most 10% extreme, and then you compute the mean of the rest. You could compute the median. I've already shared with you, of course, how to compute the median, but I haven't taught you how to do statistics for the median, right? I just told you how to compute the median. I didn't tell you how to make a confidence interval or a hypothesis test on the median, right? I didn't, because it's pretty complicated. That's why we didn't tell you. Well, we don't tell you. You can do it, but it's complicated. Quantiles. I also told you to do how to compute the quantiles, but I didn't tell you how to do statistics. Now it almost becomes a bit challenging, maybe. And there, the coefficient of variation from chapter 2, the standard deviation divided by the mean. I told you how to compute it. I didn't tell you how to do statistics on that one. What about any other thing that I could compute in some random phenomenon situation? I haven't told you yet how to do statistics, and you might need to take many classes or this lecture to learn how to do it. Another motivating factor for digging into this is, and hey, a point here maybe I should say, the theory that we used so far, and it's also present from the title of the E-Note 3, all the theory there, where we use the t-distribution and the chi-square distribution to do the job for us, is based theoretically on assuming that the data comes from a normal distribution, right? It is the normal assumption that gives the theoretical validity of using the t and the chi-square. Or, then we also discuss this magic result of the central limit theorem. Or, we just hope, as I say there on the bullet point 3, or we hope that central limit theorem is doing the job for us such that we can use all of these things anyway, even though, assuming that we hope that the n is large enough for everything having become a normal thing. We hope. I presented it as a magic result when I told it to you, and it is, but it's not the pure magic, right? It has a price. It requires n to be large. And the problem, but, in practice, when you sit there out there in your new company, you are hired by Novo Nordisk or by FOSS or someone else, you sit there with the data, and then your boss asks you, can I believe these results? Should I put a $1 billion investment based on your results? Are they correct? Are you sure? Yeah, I used the central limit theorem. Are you sure it's okay? Is it okay? Is n big enough for you to make a $1 billion investment? Is that fair enough? That's a scary question. We don't really know, right? And so far, I didn't really teach you how to find out whether it's okay. What I teach you today can be used to check whether it's okay, actually. And it is computer power that we're going to use today. So, sometimes we compute different things than the means that would theoretically be difficult to do statistics for. Sometimes the normality assumption is simply purely wrong, right? And then we might not want to hope for this CLT every time. We might want to be sure ourselves that things are okay. That's why it's important for us in this course. Before we then go to the real statistical use that all of this is sort of a motivation for and leading us to, I will use until the break to talk about simulation as a general tool, or maybe I should emphasize, for me it's by default, stochastic simulation, because that's what I'm talking about here. Simulating random variables, simulating probability distributions on the computer, how is that done and what can we use it for? With a view towards statistics, of course, but we can see it as a pure probability calculus tool, without necessarily talking about statistics, but just talking about how can we compute things within probability by the computer. That's what I'm going to share with you now. We have already seen, and I have 2 slides down, this list, just to make that clear right away. that in a way we are up and running already with this thing, the simulation thing. Because most of these distributions that you can think of, and definitely those that we use in this course, can be found in a simulation function version within R, right? We can simulate the normal distribution, the log normal, and so on and so forth. But let me jump back anyway and say, how do this computer really do this? And you can write books about that. People don't write books about that anymore, but they did some decades ago. People spent quite a bit of time on studying how should we make the computer do those so-called random numbers for us. There is a whole theory within the math area about random number generators. What kind of generation procedures should we put into the computer to make it do this for us, right? And I think I revealed, and sorry for the silly way to say it, but there is not a guy with a dice inside the computer doing it for us, right? He's not there. It's actually cheating. It's not random. But the computer can give us numbers that we cannot distinguish from random numbers. How is it done? Well, there is a so-called mathematical algorithm, random number generator, implemented. What it can do is that if you plug in one number, it can give you the next one, right? If you give it the xi, it gives you the next one. And then it can give you a sequence of many numbers, such that when you look at this sequence of many numbers, it appears completely random. That's what the computer can do for us. To do this, we also need to start it somehow. It cannot just magically by itself pop up with a number. Well, then maybe it can almost, it seems like that actually. That is called a seed. We actually, in principle, we need to start it. However, when the sort of daily use, and for you, you don't have to actually think about it too much. Because if you don't yourself, I mean, there is a seed function in R. You can set the seed. I'll show you. So you can start it where you want. But if you do not start it in R, it finds a number somewhere to plug in as a start. So it does it for you. It starts itself somewhere. But if we want to make some computations that we can reproduce exactly, we have to set the seed to start it exactly the same place. Otherwise, we will never get exactly the same results in the simulations we'll do. That's a little extra challenge here. Basically, these algorithms that have been developed for us, they would simulate in the way they are defined, in the basic definition, they simulate numbers between 0 and 1. Uniform numbers between 0 and 1. That's what such algorithms will give us. And then I couldn't help, even though we really don't need it. So I apologize to show you something you don't need, but it's a clarification theorem, this. It's so easily seen, and so it's a really, really nice understanding that all distributions in the world can be simulated explicitly from the uniform simulated numbers. And that's how it works. You simulate the uniforms because, and that's what is put in this theorem is what is shown in this picture here, exemplified by a specific exponential distribution. I have plotted the f of x, the distribution function for the exponential, specific choice of the exponential. Now if you simulate random numbers on the y-axis, that's how you should see it. I simulate numbers between 0 and 1. And that corresponds to the possible values for a distribution function. That goes between 0 and 1, right? Then if you go inverse, apply the inverse distribution function. You get numbers on the outcome scale of this particular random variable. In this case, it's only positive. So by simulating probabilities between 0 and 1 by the uniform, taking them through the inverse, you get some numbers on, that can be anything in this case, and these numbers will behave like an exponential distribution. So by taking those, applying the inverse distribution function, we have simulated data following the distribution function f. Completely general. So whenever you have a distribution function of some weird distribution that you meet in your engineering career when you've digged into the inner details of Novo Nordisk development program or FOSS Electronic or whatever you do, and you come up with some weird complicated distribution function for the phenomenon that is relevant for you, you can simulate it. It doesn't have to exist. You can just, if you can implement the function in R, then you can simulate it, because then you simulate uniform and you get the numbers. I've tried to show here. This line here simulates 10,000 exponentials of with lambda equal 1/2 that I used as an example. In this one, I explicitly use the inverse distribution function. I'm not going to show that this is exactly the inverse distribution function, but it is. And then I simulate uniform numbers and apply the inverse distribution function, which is the same as, again, simulating uniform numbers and applying the inverse distribution function in R, which is, we've learned that previously, the inverse distribution function. Px is the distribution function, Qx is the quantile function, that is the inverse distribution function. These three things I do here, 10,000 times each of them. What about means and variances? Means is 1/1/2. That's almost 2. That's the introduction to simulation, or what is it really? You're neither crying nor laughing, so let's move on to the examples, and we jump to the second part